Hello everyone and welcome to video number 2 in the magnetic circuits course. What is the magnetic circuit? So let's start. In this video we are going to cover what is the magnetic circuit, flux density, field intensity, permeability, the relationship between field intensity and flux density, pH curve, effect of magnetic saturation, and the reluctance. We are going to summarize this video at the end. So we didn't understand what they mean by this stuff. We are going to cover them one by one. What is the magnetic circuit? The main definition of the magnetic circuit is a closed path through which the magnetic flux passes. This flux flows in a magnetic material. So the magnetic circuit is considered as the main structure of electrical machines. Static machines such as transformers and relays, or dynamic machines such as motors or generators. The iron material provides a low reluctance path for the flux. Let's look for this figure here. We have iron core with certain area A, and we have a number of turns N, and there is a current injected to that one I ampere. Sometimes the magnetic circuit includes an air gap. And a good example for the air gap, like the separation between a stator and rotor in rotary machines. The magnetic field is produced by a current flowing in the coil wound around the magnetic core as explained in video number 1. So we have here a number of turns N, and there is a current I. That one is going to generate the flux phi. And here we have the number of turns N, and the current I is going to generate this flux phi. This current generates what we call it the magnetomotive force, where the magnetomotive force equals Ni, the number of turns N multiplied by the current I. And we can use this symbol to represent the magnetomotive force, or MMF. But we need to delve more to know about these symbols and what's included in the magnetic circuit and how this circuit can be analyzed. This is what we are going to cover in the next slides. What is the flux density? If we look for this magnetic circuit, we have a number of turns N, and there is a current I injected to this one. So we have a magnetomotive force Ni drives a flux phi in this magnetic circuit. This flux phi has the units Webers. And in practical or typical values for this flux should be in milliweber. Most of electrical machines, something in milliweber. So what is the definition of the flux density? If we look for this magnetic circuit, we have here a certain area A, the perpendicular area, or the flux is perpendicular to it. So the magnetic flux per unit area A is defined as the magnetic flux density. And it has a symbol B. So this B has a unit, Weber per meter square or Tesla. So let's look here. So the flux is perpendicular to this area. So this area is something like x, y. So if we multiply x and y, that one gives you the area of this rectangular. So how to calculate it? So we have area is a perpendicular area in meter square, and B is the flux density in Tesla or Weber per meter square. So the flux phi equals double integral B dot dA, where dA equals dx dy. So that one is dx dy. So that one gives you area here equals xy, the area of this rectangular. Before we leave this point, if we look for this magnetic circuit, so the area is something like that one, the perpendicular area or the area that the flux is perpendicular to. So here we are going to have this area, not the side area. So side area is not accepted. So the area that the flux is perpendicular, not parallel. Fine, we are going to remove that one. And now we are going to look for this point. If the flux density B is constant in magnitude and perpendicular to a plane of area A, so the total flux phi equals BA. So this equation is going to give us this one. So phi equals BA, and the first equation is important to us in the magnetic circuit. So if we like to calculate B, so that one is phi over A. And the dimensions here are matched. So the flux here is Weber, and that one is Weber per meter square, and that one is meter square, so that one equals Weber. We are still in the same magnetic circuit. We have here the flux phi in Weber, the perpendicular area A in meters square, and the number of turns N, and the current injected to this coil I. So the radius of this one is R. We know the relation between flux density and the flux phi is B equals phi over A. What is field intensity? The magnetic field intensity, which has a symbol H, is the measure of the magnetizing force that produces the magnetic flux phi here. And it has a unit, ampere turn per meter, or we can write it as ampere per meter. So simply it represents the strength of a magnetic field at a point due to the current flowing through a conductor or a coil. So what is the relation between H and I? So this relation is guided by Ampere's law, where line integral, closed line integral for H dot dl equals I enclosed. If we take here Amperian path, so the current injected I, and we has a number of turns n, so I enclosed equals Ni. And if we integrate that one, we're going to end up by this equation where Ni, which is I enclosed, equals HL. What's L? L is a magnetic length path. So here for this circuit, we have L equals 2 by R, which represents the circumference. That one is the average length. But if we're going to solve the problem exactly, we're going to calculate at each point. However, in this case, we can use finite element software. But if we're going to use hand calculation, we're going to calculate that one using the average length. What is the difference between B and H? Usually I receive this question from my students, and the answer is so simple. Field intensity H is the cause, how strong the source is, and flux density B is the effect, how much actually passes through an area. So still the response that they didn't understand what is the difference between B and H. So let's take an example of a water hose. And there is a pump connected to push the water on it. So this is a pump, and that one is the hose here. So H is how hard the water is being pushed by the pump, and that one is the pressure. So H is the water pressure here, represents the force. If we have different hoses, one of them is narrow hose, and the other one is wide one. So for the narrow one, we have low water flow, low density. So that one is low B. But if we have a wider one, so we have a higher B. So can we reflect that one to our magnetic circuit? Yes. If we have a magnetic circuit like this one, and we have a certain H where Ni equals HL, so we can say that H equals Ni over L. So that one is the magnetizing force. But we have different magnetizing circuits or magnetic circuits. So we have for the same H, one of them is different area here and different material, and that one is another area and another material. So for this one, for example, we have a high flux density, so B here is high because that one is better material and the wider area, and that one is a smaller area and we have something like air gap, so B here is lower. So now we have a valid question. What is the relationship between field intensity and the flux density? So we know the difference between them, but what is the relation between them? But before answering this question, we need to answer this one. What is mu? What do you mean by mu? So we are going to define mu as the permeability of a magnetic material, and it represents the relative ease of establishing a magnetic field in a given material. So now we can put mu in an equation form, where mu equals mu node mu r. So we don't know what's mu node and mu r. We are going to define them one by one. Mu node is the permeability of the free space and has a value of 4 pi 10 to the power minus 7 Henry per meter. It has a unit. And why specifically this value? So that one is experimental. So if we have two wires, each one is going to carry 1 ampere. So the force between them, the force per length, equals 210 to the power minus 7. And the radius of that one is something like r. So we have the circumference 2 by r. So that one is going to give you 1 meter distance between them. So the mu node, the permeability of the free space, is 4 pi 10 to the power minus 7. What is mu r? The permeability of any material compared to the permeability of the free space. So comparing the permeability of any material to the 4 pi 10 to the power minus 7 Henry per meter is called relative permeability. So that one is dimensionless, has no dimension. So materials can be broadly classified into two main categories, non-magnetic and magnetic. So non-magnetic materials are those for which the relative permeability is approximately to unity. So mu r equals 1. Or this one. So if we have mu r equals 1, so that one is non-magnetic material. And mu just equals mu node in this case. A good example for that one? Air. Something like the air gap. Non-magnetic materials can be classified to diamagnetic and paramagnetic materials. What do you mean by diamagnetic and paramagnetic? So diamagnetic materials where mu r is slightly lower than 1. These materials exhibit a weak opposition to applied magnetic field. For example, copper, silver, gold. And paramagnetic materials where μr is slightly higher than 1. So these materials exhibit a weak attraction to applying magnetic field. For example, aluminium, platinum, and magnesium. So in this case, we can consider μr equals 1. What about magnetic materials? Magnetic materials where μr is high or very high compared to mu naught, such as ferromagnetic materials. Can you explain more? So these materials strongly enhance the magnetic field and provide a low reluctance path. So what do you mean by low reluctance? So low reluctance, we're going to speak about that one in the further slides. But now that we are going to have a path which allows the flux to move freely. So common example for that one is ferromagnetic materials include iron, μr in the range of 5000, nickel, μr in the range of 100 to 600. We have alloys in the range of 18,000, and also we have the steel material. So these materials can be used for the construction of electrical machines such as transformers and motors. For high permeability and the same intensity, we can get a higher density. For lower permeability and the same intensity, we can get a lower density. So now we can answer the question, what is the relationship between B and H? So the strength of the magnetic field produced in the core is a measure of the effort a current puts into establishing a magnetic field, which is H, and also depends on the material of the core. So the relationship between the magnetic field intensity H and the resulting flux density B can be given by the equation B equals mu H. But, a big but here, this equation is not a linear equation. So the relationship is not strictly linear. As the field intensity changes, the permeability of the material also changes. This means that increasing the effort does not necessarily produce increase or proportional increase in the flux density. So let's take an example. Doubling H does not always double B. Since permeability is a property of the material and varies with H, this behavior is represented by what we call it BH curve or magnetization characteristics. So we need to know more. What is the BH curve? Now it's time to explore the BH curve or the magnetization characteristics for a ferromagnetic material. What a wordy slide! I'm not going to read that one word by word. I added that one here for those who like to stop the video and read the explanation. I'm going to focus on the BH curve on the right side. So when a current flows through a coil wrapped around a magnetic core, it creates MMF, which sets up a magnetic field inside the material. We call it H. We know that one from the previous slides. So once we apply a current, there will be a small H applied here. So that one is H, ampere turn per meter. Now, if you remember, H is the cause and the effect will be the flux density. So there will be a small flux density B here in Tesla or Weber per meter square. And this region number 1, we call it the initial growth. So after this region, B rises quickly. So look here. So B rises quickly in a linear manner if H increases. So that one is region number 2 where B equals mu H and mu equals mu naught mu R and mu R is constant in this region. That one is called linear region until we reach this point. So after this point, B starts to slow down. It's not going to continue linear like this one. As H increases, B starts to drop. And that one is called the knee of the curve, region number 3. We call it the knee of the curve. If you increase H more and more, so B almost after that one kept constant, and that one is called saturation region. We cannot have more flux density in this region. This is what is called the magnetization characteristics for a magnetic material or for a ferromagnetic material. Simply we call it BH curve. But there is a question now. This BH curve is genuine for all the materials? The answer is no. Each magnetic material exhibits its own unique magnetization characteristics. Let's take an example. We have an example here that we have 9 different materials. Each one has different magnetization characteristics. The question now, if we have electric machine, something like the transformer or a motor, induction motor or synchronous machine, which B point could be suitable for the design? So is that the knee of the curve, the saturation region? So now we need to know what is a saturation. So the question first, what does a saturation means? So usually my students ask me, what is a saturation? So to explain that one, we are going to simplify the idea. Assume we have a sponge. This sponge will be dry sponge at the beginning. And once we put that one in the water, so that one will start to absorb the water and fill these pores. So the initial stage is something like this one, which is the initial growth. That's like unmagnetized material start to fill these points. So we are going to reach to another point that the sponges start to fill these pores more and more and more. So water filling the pores like aligning material domains. So we have something like this region. So the flux density will be in linear manner with field intensity. Once you arrive to this one, so all the pores are filled, and after that one there is no empty pores. So in this case we reach saturation. We cannot take more water or put more water in this sponge. So no further increase in magnetism. So this is an analogy between the magnetic material and something like this sponge. So the question now, is saturation beneficial or harmful? We need to answer this one. Can we design our machine now at this region? So this is a question. Adverse effect of magnetic saturation. Let's return back to the example of the sponge. If the sponge in the saturation mode, all the pores are full. So in this case, if you are going to add more water in magnetic circuit, you are going to add more current, more H. So this means that the water will be spilled out and they are going to cause a mess. Something bad, not good. And this is the same for the magnetic circuits. We are going to have bad effect. So magnetic saturation happens when a ferromagnetic material cannot magnetize any further, even in an increase in the applied magnetic field intensity. This leads to several effects. We're going to look for them one by one. Definitely low efficiency, because adding more current does not produce a proportional increase in the magnetic flux, which leads to energy waste. So definitely you are going to have low efficiency. Overheating. Sharp increase in the current produces excess heat generation, potential damage to insulation and components. And we are going to have lower lifespan for the device. Distortion of signals. If we're going to work in the saturation mode, so the curve will be nonlinear, and in this case the AC signal will be distorted, and we're going to have harmonics. According to these harmonics, we're going to have a noise in our electrical systems. Reduced inductance. You didn't speak about inductance yet. I'm going to speak about that one in the further videos. But inductance depends on the number of turns in the reluctance. And reluctance is function of the dimension and the permeability. And if the permeability in this region, this means that this can cause circuits to malfunctioning or becomes unstable. Equipment damage. According to the previous points, low efficiency, overheating, distortion, reduced inductance, so prolonged saturation causes burnout windings and damaged cores. This leads to complete failure of electric equipment. So if saturation is something harmful, not beneficial, so where should a magnetic circuit operate on the pH curve for optimal performance? The answer is, the design of magnetic circuit should be just below the curve's knee, where the material is efficient, responsive, and not yet saturated. We are in this region, right? So what are the typical values? If we're going to design an inductor, so the range will be 0.1 to 0.5 Tesla to avoid any saturation due to the DC bias. For power transformers, the range will be 1.2 to 1.7 Tesla. And for rotary machines, the range will be 0.8 to 1.5 Tesla. In the air gap, in the electrical machines, rotary machines will be in the range of 1 Tesla. We noticed in the previous slides that you mentioned the word reluctance 2 or 3 times, but you didn't explain it. So let's start from the magnetomotive force F equals Ni equals HL. And H has a relation with the B, flux density. So we can write this equation as Ni equals B over mu L. But B has a relation with the flux phi in Weber. So we can rewrite this equation as Ni equals phi L over mu area. L is a magnetic length path, mu is the permeability, so mu node mu node equals 4 pi 10 to the power minus 7 Henry per meter, and mu r is the relative permeability, where A is the perpendicular area. So this term, L over mu area, we're going to define that one as a reluctance, so which is a special letter R here. L over mu node mu r area, and it has a unit, ampere turn per Weber. If we're going to measure the reluctance in the air gap, so mu r equals 1, so that one equals L over mu node area. So it is called the reluctance and is defined as the measure of resistance to the establishment of magnetic flux in a material or magnetic path. Some textbooks like to call it S, but I'm going to use this letter R. So the magnetomotive force equation can be rewritten as Ni equals HL equals phi reluctance. But if we have multi-windows in the magnetic circuit, so to make this equation general, so Ni equals sigma HL equals sigma phi reluctance. Now we are ready to analyze the magnetic circuit. So let us summarize this video. If you have a magnetic circuit like this one with or without air gap, so we have a coil with certain number of turns N, and there is a current injected in that one, I. So Ni is called the magnetomotive force. So that one is going to cause a field intensity H, depends on the magnetic length path, where Ni equals HL. In this case, you are going to have a flux phi in Weber, and the flux phi applied to a certain area, perpendicular area A, we are going to have a flux density B. So the equation here, guided by this one, that Ni equals phi reluctance, or Ni equals HL. But in general case, if we have multi-windows, we can say that Ni equals sigma HL equals sigma phi reluctance. So the main equations for the magnetic circuit, that phi equals BA, B equals mu H, and the reluctance R equals L over mu node mu R area, and Ni equals sigma HL or sigma phi reluctance. What will I watch in video number 3? In video number 3, we are going to cover the analogy between magnetic circuit and electric circuit. See you in the next video.